I'm Neil. I'm currently the data science team lead at Trends. So, for some, just a little bit of context, at Trends, we wanted to develop a tool that could measure the public's sentiment. It could be a sentiment about a politician, or a sentiment about a celebrity, or it could be a sentiment about a product. For instance, Universal or Rubina wanted to release a new product, and they want to know how the public is responding thus far. And in order to quickly get that public's pulse, we wanted to leverage social media. Now, along the course of solving that problem, we had some roadblocks. Number one is that since we want to use it locally, we want to deploy it locally, our model should be able to account for local language, local and some other Filipino dialects. So that's one. So the consequence is that there's a bit of lack of training data for that. In text-based problems and sentiment classification problems, there is significant amount of freely available training data, but mostly for English, but not so much for Tagalog. So that's one roadblock. Another is that if we want to build our own, that's still a problem because of a lack of personnel in our team. So at that time when I was working on it, we were just 5 in the data science team, although currently we are 7. Although we do have other teams, the data engineers, the visualization specialists, and software developers, but they're also working on their own respective projects. So essentially I was a one-man team for that particular project. So I had to innovate. I had to think of ways to get over those predicaments or roadblocks, and that's what I'm going to talk about. So along the course of solving that problem, we will discuss, briefly go through word embeddings, what they are, and what transfer learning is, and we'll discuss the technique for merging word embeddings, and we will explain why would we want to merge word embeddings. And finally, it's about we will discuss about leveraging the merged word embeddings to develop a framework for transfer and continually adaptive text-based, in general text-based machine learning problems, but for this specific project, this is specific to sentiment classification problem. All right. So what's a word embedding? In machine learning problems, most machine learning algorithms require that your input is in numeric form. You cannot input data in text form. So a word embedding is one form of representing your text data into a numeric form. It represents it as a vector. There are other forms like TF-IDF, but the advantage of using word embeddings is that it models the concept of meaning. So it is an unsupervised feature learning method because given only a corpus of text, a set of text, you do not have to manually label training data. You just feed it. You just feed the text corpus, and the algorithm itself learns the most optimal vector representations for each word, and at the same time incorporating the concept of meaning that words with that are closer in meaning have vector representations that are also in proximity to each other. For instance, in a properly trained word embedding, the words king and queen should be represented as vectors that are in proximity with each other, as well as the vectors for man and woman. And not only that, the implication of this, of modeling the meaning, is that the word embeddings are also able to model other linguistic operations like analogy. For instance, as we will see later on, a word embedding would be able to answer questions like, if king is to a man, queen, in the same way, queen is to a woman. So other analogy questions like that can be answered using word embeddings. So what's the advantage of using word embeddings as compared to more standard techniques like TF-IDF? It has been found that aside from being able to model meaning and model the process of analogy, it tends to produce better performing models. And more important, the key advantage of word embeddings really is that you can have a labeled supervised training data like sentiment classification problem on a fairly limited vocabulary. And it is able, as long as the vocabulary, let us distinguish between the vocabulary of the supervised learning model itself and the vocabulary of the embedding layer, your word embedding. So, you can train your supervised model on a fairly small set of words, small vocabulary, as long as your word embedding has a significantly larger corpus. Then you are able to, essentially, that's what, you are able to transfer the knowledge from the original training words to the words outside of the original vocabulary. So that's, in that sense, that's where transfer learning comes. So, these are the two methods for arriving at a word embedding. A word-to-vec and GloVe. A word-to-vec is developed by researchers at Google. It's a predictive model wherein, given a corpus of text of data, it determines pairs of words that are within the context of each other. For instance, in the given sentence, produces word embeddings by constructing a supervised model. So it means that the word constructing is within the context of the word and it is within the context of the word by, because it appears within the neighborhood of the words by and a. So if you build a predictive model with that input, given the words constructing and the word by, is the word by within the context of the word constructing? Yes, because it is in the neighborhood, and the measure of neighborhood can actually be adjusted. Usually it is within 5 words, but you can tweak it to a little bit less or a little bit more. So they found that if you train a supervised model using that technique, and the thing with neural networks is that the initial layers are actually automated feature learners. Are you guys familiar with that concept? That the initial layers of a neural network are essentially automated feature learners. So when you train a supervised neural network using that corpus of text in the context of word context pairs, then they found that they will come up with vector representations of the words that represent the meaning, wherein words that have closer in meaning are projected into the vector space that are also in proximity with each other. So another technique for arriving at word embeddings is the one developed by the NLP research group at Stanford called the GloVe. GloVe is a count-based model wherein it still considers the concept of context or within the neighborhood of each other, but for instance, it will create a word-by-word matrix that represents co-occurrence. So for the for the words constructing and by, it creates a matrix that quantifies how many times the words constructing and by appear together within its neighborhood. So you now have a word-by-word matrix, but if your vocabulary is, let's say, more than 10,000, then the vector representations would be 10,000 dimensions, which would be too large, and it will take a lot of time for training. So the additional step for Globe is that you perform a dimensionality reduction on 10,000 by 10,000 matrix. It could be via matrix factorization. So coming from a word by word matrix, you will arrive at a word by context matrix. So usually it's in a range of 100, so 100-dimensional vectors, or 300-dimensional, or 500-dimensional vectors. Now, the transfer learning is usually mentioned in the context of image processing problems. Because in images, the features are actually common, regardless whether you are training for classifying between cats and dogs or classifying between cars and persons. The individual pixels are actually common between those two problem sets. So transfer learning is often mentioned in that context, in the context of image. But I realized along the course of working on this project that transfer learning actually can also be used in the context of text-based problems, which is essentially by using word embeddings, using vector representations of words that have been trained as an unsupervised model and then added as an initial layer. So it's essentially like if you're training your data, if you trained your model from an initial set of data, it is able to infer to other set of data with whose words are not included in the original training set. So that's where transfer learning comes in for the context of text-based problems. Now, so let's talk a bit about merging word embeddings, and later on we will discuss on why would we want to merge word embeddings. Now, as I've done a bit of literature review, but not very rigorous or thorough literature review. And what I found in the literature is that they do have current techniques for merging word embeddings, but the context is that given two languages, like for instance, you have a corpus for the English language, you have a text corpus for the Spanish language. They independently train a word embedding for the English language training data. So they project the English words to some vector space, and then independently they trained a different model, a different word embedding for the Spanish language text data. So you have two vector spaces, and they want to merge those. So what they did is that they use a dictionary for some set of words. For instance, for the word morning, in Spanish it is mañana. So they use a set of those reference. They use those dictionary words as reference words, and then rotate the other word embedding in order to correspond with the English word embedding. But in our context, in the context of my project, we are working on Filipino data, but the one peculiarity of us Filipinos, especially in social media, is that we interchange both languages a lot. So we type both in the local language and English language. So that can actually be leveraged. I realized that I already have a text corpus that has both English and Tagalog words, where in the case of what I found in the literature, the context is that other Spanish people rarely write in dual, in mixed languages. So I had to innovate a bit in my case. I realized that in the context of our project, I can actually skip that step. So I will describe that technique of how I merged a word embedding. Now, the key insight here is that given the same text corpus. When you say a text corpus, you say you have a set of documents with all the words, all the sentences, all the paragraphs. Now, given that as input, and you train a word embedding, and some other person trained a word embedding using that text corpus, unless you both initialized with you seeded with the same number, you are not assured that you come up with the same vector representations of the words because of the nature of the randomization nature of training machine learning models. If you are the only one working on it and you can assure that you initialize it with a random seed of a seed number of the same, then you can be assured that they are roughly similar. But since in our context we want to leverage existing word embeddings trained by Google, then we cannot be assured that they seeded it with the same random number as ours. So, but what you can be roughly assured of is that even if your vector representations are different, the relative distances of those vector representations are retained. So that's what is being conveyed by that graphic. So in one word embedding, the words hate, admire, and love might be represented as these vectors, and in another word embedding, those words might be represented by different vectors, but you can leverage the fact that relative distances of those words are retained precisely because word embeddings, in training word embeddings, you are assured that you retain the idea of that words that are closer in meaning are represented by vectors that are in close proximity with each other. So how would you leverage that? For instance, the word Lodi hasn't been in existence a few years back, right? So how do you, if you have a standard word embedding like trained by Google, and then you have a separate corpus of text with some common that has an intersection set of words with another word embedding, but you have newer words in the other word embedding, and you want to merge that with the original word embedding. So visually, it's very intuitive, right? It's very intuitive. You just visually measure the relative distances and then you project it. So that's roughly very intuitive in visual form. But how do you implement that? How do you execute that in code? One technique of doing that would be a more sophisticated approach would be to derive a rotation matrix. A rotation matrix is wherein given a vector, you multiply that vector with this matrix, then it is rotated in some other form to another vector space. But that would require a bit more sophisticated techniques like optimization techniques. But in the context of research in the academe, that would be the more appropriate approach. But in the context of the industry where you have urgent deliverables, you have to find ways to execute it quickly, albeit in a less rigorous manner. So what I took is that I had to think of a way to implement it in a less rigorous way, but easier and faster. So I call that approach a hacker's approach because it is less rigorous, but it does work. So how do we do it? So again, as described earlier, we use common or standard words as reference words. These are words that are present both in the original word embedding and the custom word embedding that you trained. And then, for instance, in this case, we use the words hate, admire, and love as reference words. And then we compute the relative displacement vectors of the new words. For instance, for the word Lodi, how far is it from the reference words hate, admire, and love. And then we project it to the other word embedding by adding the displacement vectors. And then you average over those several vectors that is arrived in reference to the reference words that you set. Now, having described that process, now, why would we want to merge word embeddings? The reason being that there are pre-existing pre-trained models like Google and Stanford. Stanford has a word embedding trained on Twitter data, and that word embedding is trained on a more more powerful computing resources, and they had a lot of time spent on that. And I want to leverage that because it is a more robust model. But at the same time, I also want to incorporate newer words, especially in the context of social media. Newer words come out every so often. So how do I leverage both? How do I enable myself to leverage the standard word embedding trained by established institutions like NLP, and at the same time incorporate newer words? That's where merging word embeddings come in. So I used standard word embedding trained by Stanford, and then I trained my own custom word embedding on dataset scraped from Twitter, and then I merged those in order to be able to add new words to the original word embedding. And another advantage of course using word embedding is that you can leverage as I mentioned, there are actually a lot of off-the-shelf tools that can deal with sentiment classification problems. One of those off-the-shelf tools is VADER. It lets you, it is a rules-based sentiment classifier. Now, you can leverage not just VADER, you can leverage practically any off-the-shelf tool, but the thing is those tools can only tackle English data. So that's where merging word embeddings come in. Again, as I mentioned, this is where merging word embeddings enables you to do transfer learning. That the training data that the set of sentences in English, mostly in English, that you label using an off-the-shelf tool like VADER, you can impart that knowledge or transfer that knowledge to the rest of the sentences in your corpus. That it involves words other than English. It could involve Tagalog or other dialects like Bisaya, Ilocano, and others. So that's VADER is. This is how just describe. Go over how VADER implements. VADER assigns a set of assigns a real number for each word, ranging from -4 to +4, and then it combines that using some heuristics like punctuation, capital. If there's a punctuation, it is magnified. There's a capitalization. If it's a negative, it is magnified. If it's positive, it is magnified. And there are also degree modifiers, negator words, and polarity shifters like that and however. Now, this is having had merged word embedding, and these are the steps that I use in order to create a continually adaptive model wherein, imagine a scenario wherein you have a sentiment classification model running in production, but in 5 years or even 3 years from now, do you think it's still accurate? Do you think it's still relevant? Who knows what other words vice ganda might come up in the next few years, diba? So especially in social media, there are a lot of words coming in. So in 5 or 8 years, your model will be not as accurate. And what do? One option would be to retrain your model from scratch, but that would be a lot of work. But the technique I developed is that you can do away with retraining a model, but you just have to update the embedding layer of your neural network model with the newer words. And then there's a way to, in Keras at least, I'm not familiar with TensorFlow of how you can do it, but in Keras, there's actually a way wherein you can replace the layer of your trained neural network and then retain the other layers, the weights of the other layers. So intuitively, this is how it works. So for instance, you have a model, you originally trained your supervised model in containing this set of vocabularies. In a few years, in 2 or 3 years, there are new words coming in. So instead of retraining the entire model, what you do is you just replace the embedding layer. You just train a new customized word embedding, incorporating those newer words, and then you merge it with the existing word embedding that you have, and then you replace that. You take the old word embedding and you replace it with a newer one. So essentially what you did is that you added the newer words vocabulary to your embedding layer. So otherwise, if you do not do that, the newer words like Lodi, if the embedding layer does not find it in its vocabulary, it is assigned to a random vector. Actually, you can set it to be assigned to the 0 vector, or you can set it to be assigned to the random vector. But if you incorporate those newer words, it will no longer be assigned to a random vector, but it will assign to the new vector representations that you learn. So every couple of years, you can add more and more newer words to your supervised neural network model without having to retrain the entire neural network. So if there's still time, we can take a look at the Jupyter Notebook. So just go over this quickly. My apologies for the messy code. I'm not primarily a programmer, so if there's a workshop here for coding standards, then I might have to attend. But this is the code I used for merging word embeddings. So I leveraged the Globe standard word embedding trained by NLP researchers at Stanford, and then I trained my own custom word embedding. And then I found I got the words that are in the new custom word embedding that are not present in the original word embedding, and then I found the intersection word set between the two word embeddings, and then to use as reference words, I derived the most occurring words that are present in both word embeddings, and then I use those as the reference vectors. Which is the one I showed earlier. And then I computed the relative distances of the newer words in reference to those reference vectors. Now, so just a little bit of demo. This is now the merged word embedding, and I just want to show how it works. For instance, the word Petmalu is obviously not in the vocabulary of the word embedding trained by Stanford researchers. But in the word embedding, since I merged my own custom word embedding, it is able to infer that the word Petmalu is similar to these following words like nakaka-proud. This is the most relevant word here. Although it might be not as accurate because in this particular case, I had time constraints for learning. I just used 100 words as reference words, but in production, I used more than that, like 1,000 or more. So even at that scale, it is already able to infer synonyms. And on top of being able to infer synonyms, it is also able to infer analogy. So for instance, a king is to a man in the same way that queen is to a woman. So in this case, to demonstrate that it is able to work on local dialect, babae is to GF as lalaki is to BF. So it is able to hindi yan rules-based na minano-mano kung i-match. It just computes for the vectors that are closest in proximity with the word lalaki relative to. All right, I think it's about time, and we may entertain some questions.
Any questions? All right. This is yours. Okay. Okay, where was the question? Okay, so just two. Him first and then you.
Me first? Yeah. Okay.
Hi.
Hello.
Hi.
My question is, how do you know that the two embeddings are at the same scale when you're merging them? Like, what if one is so much longer than the other?
No, you have to choose the word embeddings. For instance, I used the 300-dimensional word embedding trained by Stanford, and I had to train my custom word embedding with the same dimensions. You have to assure that they are both of the same dimension, of the same scale.
Yes, yes. But I mean the vector lengths, like because you're using relative distances.
Yeah. That's interesting question because I haven't actually accounted for that. But if you use, instead of relative distances, if you use the cosine distance, which is the angle, because in implementing, in inferring synonyms, you actually do not measure the relative distance, but you measure the cosine similarity, which is the measure of angle between the two. So downstream, it will actually be compensated because when you use it in the context of arriving at synonyms, you only compute for the measure of angle between the two, between the vectors instead of the actual relative distances.
Okay, thank you.
Hi, wonderful talk. So my question is, you mentioned that when you're encountering new slang words, you just kind of change the embedding layer, if I remember correctly, and you don't have to retrain the model.
Mm-hmm.
So my question is, what are the instances where you really have to retrain the model? So like, what?
That's interesting because within a span of years, what will change really is just the presence of newer words. But the structure, the syntactical structure of the sentences that are negative, the syntactical structure of sentences that are positive are roughly the same. Mag-iiba lang yung words. And my opinion is that you don't necessarily have to retrain the entire model. You just have to update the vocabulary of your embedding layer. That's just my opinion. I haven't verified it rigorously, but I'm just hazarding a guess for that.
Cool. Okay, there's another question. Can you please pass the microphone?
Hi. So I'm Pepe. My question is, it's a bit similar to the question of in scale, but it's for me the more concerning thing when it comes to merging the word embeddings would be how do you check whether or not the two embeddings are just different rotationally? So let's say let's say one word embedding is just reflected upon one axis. All of the relative angles would be maintained, but if you rotate it to the other embeddings, and
yeah, that's actually one of the key assumptions I mentioned earlier. You cannot be assured that you arrive at the same vectors, but assuming that trusting what is stated in the literature, that word embeddings retain the concept of meaning wherein, regardless of the absolute vectors, words that are close in meaning are also represented by vectors that are in close proximity with each other. So I assume that to be true. So that's one of my key assumptions. If ever that is not that the method I use is not does not abide by that assumption, then perhaps that's a critical flaw. But empirically, when I check my model, when I look at the synonyms, when I look at the performance of the sentiment classifier, roughly it does make sense. It does make sense. So I was hoping those key assumptions were abided by.
Oh no, my question was, even if the key assumptions are held, you might have problems with just rotating it. So example, your initial example of the three vectors. If you flip it by its, if you flip it by the y-axis, all of the relative angles would be the same, but you won't be able to transpose to rotate it so that it sort of conforms.
Again, it's in the context of this project. There are urgent deliverables, and this is. I acknowledge that this is not. That's why I put that as one of the final remarks. That a call for a more rigorous approach, because I acknowledge that this is more of like a hacker's approach that is kind of works, but in a faster and quicker manner instead of a very rigorous, academically rigorous approach.
All right, yeah. There's another question here.
Hi, great talk.
Hi.
I learned a lot. Hey, so does this technique work with words that simply have no translation between languages? So there are languages, there are words in some languages that just don't translate, or there may be words that are in non-Latin character classes. Does the same technique work here?
I cannot assure that, because the assumption here is I am working on a Filipino dataset wherein we mix English and Filipino fairly often. So even if the word, the Filipino word does not have a direct translation to an English word, but since they occur in the same text corpus, the relative meaning of those words can still be inferred. But in the context of other languages, like for instance, the word Schadenfreude in German does not have a direct one-word English translation in English. It takes you a lot of words to convey the meaning of Schadenfreude, which is finding pleasure in some other person's suffering. So you cannot represent it as a single word.
Yeah,
So,
in fact, that was going to be my next example. Like in some of the European languages, there are these very
there are a lot of
words.
words that you cannot translate. No two languages can be mapped one-to-one, actually. There would exist, you can always find a counterexample wherein that word does not have a direct.
How big is the overlap set that you chose?
I scraped for around 9 million tweets, but there are a lot of retweets in there. So the unique count is around 6 million tweets.
Cool. Thank you very much.
All right.
I'll get back to you. Take one over here.
Yes, good afternoon. Again, very good talk. So by the way, we're from Takral 1. So before I go to our question, I just wanted to add on top of the question a while ago for completely remodeling the model. I think my thought on that is that if after some time, so I agreed there is a time dimension to that where maybe after some time the core words might change. So the methodology of adding on top of the existing trained model might not be reliable because, for example, a word that is used as reference may have already changed entirely the definition, right?
It may have shifted.
Yeah, it may shifted because generations, etc., or the culture has changed. Now, to move on to our question, for this model, have you tested how it works against sarcasm?
Actually, I did. I can show you. For instance, the word. Let me just get back. Instance, the word gago alone, excuse my language, is classified. It is a bad word for the foreigners. It is a bad word in Tagalog. But if on top of the word gago you add a smiley, it is essentially sarcasm. So it is able to detect that it is actually, because you can use that word playfully among your friends, diba? If the word gago alone can be classified as negative, but if you add either a smiley or the word ha ha ha, it is now sarcastic. So, in fact, I've actually tested for that, and there are some instances wherein it cannot detect sarcasm, but fairly, in a fair amount, to a certain degree, it can.
Hello. I was actually similar question, but anyway, I have a new question. How does it? Can you detect emojis?
Yes, it can. Again, as when you add the smiley, because the off-the-shelf tool I used, VADER, it actually accounts for emojis, and even quotation marks like several punctuation marks.
All right.
So that knowledge is transferred to the custom model I trained.
Other questions? All right.
Hello, I'm Almer Mendoza. Ang question ko lang ay, do you have plans? Kasi isa sa your first point a while ago was there was not much enough data here locally for Filipino dataset. Do you have any plans to open source your embeddings just in case you can expand on it if ever?
That's something that can be considered, but I haven't thought of it. I haven't thought because I work on this in the context of a company project. Kasi so perhaps who knows? And if that I'll take that as an opportunity to plug in. If you want to collaborate in some capacity collaborate with me, then I'm putting my email address here, neilibo@gmail.com.
Other questions? Yes.
Gino, I see that there are two methods for training, right? It's the conventional, which is retrain all the datas, and putting the new datas on top of the core datas.
Yeah.
So the question is, what is the difference between the accuracy between the two methods?
I would guess the original method of retraining the entire thing would perhaps be more accurate, but it will take much more effort than the other technique, wherein you just replace the embedding layer.
I agree. I'm just kidding. I don't really know. Other questions? Other question? Yeah.
Sorry, I have one more question. My question is on the data itself, because Twitter has a lot of, like, maybe duplicate tweets, like if it's for a certain celebrity or whatever, if it's
Yeah.
or if it's like trolls or bots by Russians or whatever. So do you filter out those kind of data where they tend to be repetitive, or?
I have not filtered that out, but on the contrary, a retweet is actually a measure of how that sentiment resonates with the rest. So even if it's a duplicate, if it has been retweeted a lot of times, then it conveys that people agree with that certain sentiment. So in a way, you don't have to account for those duplicates because it has been the fact that it has been retweeted, it means that those people agreed with that sentiment and it should be accounted for. Diba? The more retweets a tweet has, it should be weighted more, which will be reflected in your data set. Intuitively speaking.
That one I agree and I understand. All right. Other questions? Just taking one last. All right. Thanks, Neil.
All right.
Excellent talk. Let's give him a round of applause.